All right, good morning. Having some slight technical difficulties here with the projector. So I think maybe it's coming back on. I rebooted this little thing that talks to the projector. I don't know if I was supposed to or not, but it wasn't really responding, so I did. Looks like maybe we're good now. So I was going to start writing on the actual board here for a moment and see how that went, but maybe we're good. Maybe. And maybe not. Okay, so what I'm going to start doing is I've got my slides up for anybody online, but I'm going to write the equation up for where we left off about BOD, checking a BOD in a bottle. And by the way, happy Thanksgiving. Welcome back. Sorry, I'm slightly late here to troubleshoot these problems. I might need to call IT in a minute if this doesn't work. Okay, however, we left off right before an example problem, so I want to set that up on the board for you if we don't get the projector going. That'll give you something to do while I fuss with the technology. So I'm going to work on that for a moment, which also probably means I should use my other mic. So hopefully that works. We left off talking about the BOD in a system where we had both a seeded dilution water and the wastewater itself, right? We talked about how when we dilute the wastewater, now we don't have enough microbes, and then we have a problem. So we said we can look at the wastewater plus dilution. If we want to find the BOD of the wastewater, we look at like the actual combination. So we'll say BOD initial, and I'm gonna make a little more over here. We would say that's the DO initial of the primary bottle. We have two bottles. DO initial minus DO final. All that minus what's in the other bottle. So this would be the mixture, and we have this other bottle with just dilution. So then we have minus what's in the dilution, which we said that's going to be what's called BI minus B final, and that's going to be times this 1 minus the dilution factor. So 1 minus P here. Put all of that divided by P, and that's our equation, right? So that's kind of where we left off last time. And then we said we'll have an example problem using that. I'm going to read it, and then I'm going to write up the information for you all. If you do have a laptop, feel free to check the slides. This is slide 10 of the slides that we were working on last time, or look online even. Okay, it says a test bottle containing just seeded dilution. So we'll say seeded just the seeded dropped by 1 milligram per liter in a 5-day test. A 300 milliliter bottle filled with 15 milliliters of wastewater and the rest seeded dilution water experiences a drop of 7.2 milligrams per liter in the same time period, so in 5 days. So the question is, what would be the 5-day BOD of the wastewater? So we're looking for the BOD 5 of the wastewater in this question. And we are also given this information. So mixture is 15 milliliters of wastewater in 300 milliliters, and this drops the DO by 7.2 milligrams per liter. Okay. So we're all happy that I don't normally use the chalkboard. And you can work on that for a couple minutes while I call for help. Hi, you need some help in a classroom in Turin? The panel that connects to the projector is not functioning. It's on, but yeah. Okay. Okay. All right, thank you. Okay, so the entire building's having this issue. So we're not gonna do much on the touchpad today, I think. So I'm gonna adapt as best I can for everybody until we get the change there. Do you guys get a handle on this problem? Okay, so like I said, this is not going to be ideal. Fortunately, I have some previous notes that I've done with the same slide set, so I can probably post an old set so you have something similar for your record. And I'm going to do pretty much most all of it on the board from here as best I can. All right, so let's take a look at this problem. When we fill in the pieces here, we can say that when we look at the mixture versus the dilution, and we're given some amount of drop, well, we can actually plug in the drops in each of these. So even though we don't know the initial amount in either case, we could assume one. We could say, okay, maybe it's 10 milligrams per liter. Or we could just say, well, it's the initial minus the final, that's a drop. That's how much it dropped, right? So we could put in the 7.2 milligrams per liter here, and the 1 milligram per liter over there. And then really we have almost everything. We just need to check the dilution amount. And so it's 15 mils in 300 mils. And actually the problem itself says this is sometimes expressed as a 1 to 20. If you do the math, you'll see that that's, you could express it as 1 to 20 or 1 over 20. And that's P. And with that, we could say it'll be 7.2 minus 1, but that's minus 1 times this 1 minus P. This should be 0.95 right there. So P being 0.05, that's 1 in 20. So 1 minus 0.05 would be 0.95. So this is really 7.2 minus 0.95. All that, we can put that P to the top and say that's times 20. So we'll end up with BOD of our wastewater is equal to 7.2 minus 0.95 times 20. Okay, so I'll just get a calculator real quick and we'll show that. So that'll give us 6.25 times 20 is 125. Okay, so there's kind of just a bit of practice there. Hopefully pretty straightforward. So next thing I want to talk about is essentially, now that we're going to send some sort of wastewater downstream, what does that end up looking like practically? And so what we'll see essentially is we can take a look at what's going to happen to the dissolved oxygen, what's going to happen to the amount of substrate, what's going to happen to the water as we flow downstream. So we'll take an example of some sort of river flowing downstream, and we've got some wastewater discharge added right there. And then if we make some assumption that it kind of mixes with the river, and sometimes in fact we'll have effluent discharges that intentionally spread it across the river. We might have instead of just one outfall pipe, we might have a pipe that seeps out through the whole thing or discharges through the whole pipe. So sometimes there are intentional mixing conditions like that. So anyway, if we draw it that way and describe it that way, then we have a situation where we can treat this kind of as a plug flow. Okay, so this will look a little different if we were to do it in a lake or a pond. So for the sake of our BOD stuff, we're really only going to consider it as if it's a plug flow system. That also means that we can track the time in a way that as if it's distance, right? So the length of time downstream is pretty much proportional to the distance. That'll be kind of convenient in case we want to know at what point downstream do we have a problem, when is the BOD going to be the lowest, for example, or when might we have, where should we look for this wastewater discharge to really be an impact. Okay, so with that in mind, we can look at a couple things as a function of our time or distance. So we can write distance in x. And that would be essentially our dissolved oxygen level or our substrate level. So I'm going to write dissolved oxygen, and I'll use a second color for our substrate. And that would be like our TOC. We could measure perhaps with total organic carbon or something to that effect. So for the dissolved oxygen case, we can imagine we'll have some sort of saturation level, where that's going to be our water when it's saturated with air, with the oxygen in the air. And at time 0, or distance 0, we've just discharged our wastewater, and typically we aerate our discharge right before we aerate our wastewater right before we discharge it. So the wastewater itself should have a pretty good oxygen level at that moment. We don't want it to have already consumed a bunch of oxygen and then send it away having an immediate dissolved oxygen impact. So we aerate it right as we're sending it out, and then from there we'll have some oxygen demand. Now typically natural waters have some oxygen demand already. You know, just natural biological life and stuff are going to be causing some demand. And so we probably start our oxygen curve somewhere near saturation, but a little under. So then if we track after wastewater discharge, we will typically have something that ends up looking like this, where we have some dip as the wastewater, whatever organic material is left in there, biology is consuming that and taking it away. And then eventually that substrate diminishes. And so if we track the substrate, we would see, you know, kind of a similar thing, that it is being consumed over time, right? So it would be, and actually, I guess I probably didn't draw that very well. It's probably going to be kind of an exponential decrease rather than this curve looking better. Already missing the eraser function on the. It probably look more like that. Okay, so that would be just decreasing over time, kind of as if it was in a batch reactor. Should be first order with respect to how much substrate's there. And so that would be kind of the way it looks for the dissolved oxygen given some amount of substrate. Now, one thing to note here is we could also identify another term here that we would call the deficit, oxygen deficit. That would be directly related to the oxygen demand, but it would really just be the difference at any given point between the saturation level and the current amount of DO, right? So we could have another D here, D at some time t for deficit. D is deficit. And now that I'm thinking about it, I'm going to rearrange a little bit for the people online. Give them a better view here. Actually, I don't think I can. Depends on how far this code goes. Okay, maybe. Okay, so that oxygen deficit, I'm highlighting that because that will essentially give us a situation where the thing that's driving oxygen back into the water in part is that deficit, right? So if you think about kind of how gradients work typically, the steeper the gradient, the higher the force, whether this is osmosis, like a chemical force to try to get back to equilibrium. That gradient is really what drives the re-aeration here. So if we give it a lot of mixing, so if there's like a waterfall, rapids, that would improve the opportunity for this gradient to act, essentially. So the rate at which oxygen is going to increase back into solution will depend on this deficit and will depend on that kind of mixing conditions. Also depend on the temperature, because that's the saturation level. Okay. All right. So we've got a couple terms here I want to talk about next. So as we think about how exactly to model this, there's a few things that come into mind in terms of how we can talk about the amount of substrate that's left, how can we model this so that we can model what's happening with our dissolved oxygen as we go through our system. Okay, so that's our goal right here, is to say, how can we achieve some insight on what this is going to look like? Because one of the things we might be worried about as well, at what point do we hit this lowest spot? And how low is that lowest spot? So that's kind of one of our targets, is to understand the worst case scenario, when it happens and how bad it is, and overall be able to predict, given this wastewater discharge, how does the outcome look? Right? That's kind of our goal. Okay, so then we can define a term. You know, one of the tricky things is our BOD here, the substrate, is changing over time. This is what's causing the deaeration, right? So we have several rates here. We have the oxygen consumption. I'll call it deaeration. That's probably not the right term. So deoxygenation, I guess. That's a downward movement for the oxygen. And then we have reaeration. Increasing the oxygen back. The deaeration is going to be kind of synonymous with, or at least dependent on, the substrate consumption. But the substrate consumption is changing over time. So we need to handle on a couple things. All right, so we need a couple things here, and I'm going to start by defining one more term that relates to the substrate, and that is the amount of substrate remaining. We're going to call this L. We'll say L is substrate remaining. And we could say L at time t, or so L of t, is substrate remaining at some particular time downstream, right, or distance. Okay, so this can get confusing if we start thinking about like BOD5 is 5-day BOD. Try to pause there and say to yourself that this is going to be distinct. This is going to be a separate situation where we have, you know, we could let it go for 2 days and then measure a 5-day BOD, right? So our BOD measurement, that's just going to be what it is. That's a 5-day thing. That's just going to sit there. If we have we can measure the amount remaining after 5 days, but that's going to say we wait 5 days and then do a 5-day BOD test, right? So try not to get too confused here. What we're saying is this is the amount of substrate remaining in the water after some amount of time that biological activity has been happening. Okay, so then we can also describe or use a term for the amount that's right here. So L naught would be the total remaining, the total substrate remaining at time 0. That's the total amount of substrate we've ever had. We could also say that this L0 is essentially the same value we'd get if we did an infinite BOD test. We did a BOD test for an infinite number of days. Right? So this is the ultimate BOD, or the, let's see, I think I have the term for it. ultimate BOD. And this one's actually not just the wastewater. This is the wastewater mixed with the river. So we have whatever BOD happened to be in the river, plus whatever BODs in the wastewater. You mix them, you mix the flow rates, and then combined we have this initial condition. Right, so this is from the Q river plus Q wastewater and their respective BODs or substrate amounts. Okay, so then we can relate each of these. We can make a rate expression for how this amount changes with time. And really, again, this is the amount of substrate in our river that's causing the deoxygenation, right? So to map that, we need to understand the dLdt, right? So that's where we're coming from with that. We can say this is going to be equal to negative KT, as we often do. And, excuse me, KLT, right? So that would be first order with respect to L, and that would be kind of where we would derive our system. So that's pretty straightforward. We've done this a bunch. And so this K then would be, so be a BOD removal rate constant. And the other thing we could say, let me just make sure. Another thing we can say about these guys here is that we could say the L naught is going to be equal to the L at time t plus, so that's the how much has been remaining, plus how much has been consumed already. We'll say BOD of the initial thing. So if we checked at 3 days, we could say that's, the ultimate's going to be equal to the amount remaining at 3 days plus the amount that had been consumed in 3 days. So in that sense, hopefully this is maybe helpful. This is remaining, and this is something we measured that was that much consumed. All right, so then we need to look at some stuff about how to reoxygenate. So if that little panel of the board is all about deoxygenating, removing the, looking at the substrate, how that's, well, I guess that's not deoxygenating. That's looking at how much of the substrate's there, which does tell us something about the deoxygenation. Then we need to look at how this is affecting the oxygen content, and then what else is affecting it in terms of how much oxygen are we adding back. I'm trying to balance a little bit so that some of this is captured and visible on the screen, but I can also see the slides. All right, so to look at the deoxygenation then, like I said earlier, that's going to generally be related to the rate at which this stuff is being removed. And so we could take a look at, we could define some sort of deoxygenation rate constant, K lowercase d. These are all in the notes, so you will find the formulas that I'm about to put up and their definitions. But just wanted to let you know there's a K with no subscript here for the BOD removal, and we have a K with a D as a subscript for the deoxygenation. In per time units. And then we'd have, and usually that'd be per day. And we could define an overall rate then. So R of D, that would be our deoxygenation rate constant, or excuse me, rate. And we can define an equation for that. So our equation here, RD, would be equal to ultimate BOD times this KD times E to the negative KD times T. So that is essentially coming from the rate at which substrate is removed. There's a little bit of math between there. I'm not going to bother with digging into the derivation there with you. But essentially we go from knowing how the substrate is changing to, okay, well, how does that impact the amount of oxygen being removed? Well, that's going to decrease over time. So the amount being removed will decrease over time, has some sort of starting point, and then from there, it's going to be less and less and less, given that. So there's a bit of derivation there, but it's coming from kind of the same spot. Okay, so then we want to talk about reaeration. And this is largely a physical process. You could kind of consider that gradient that I was talking about with the deficit. That's sort of a chemical thermodynamic type of process, but it's also very physical in the sense that it's pretty much diffusion, right? So you could think about maybe some of the chemistry there for equilibria, all that, but generally we would think of this as a physical process that's going to be proportional to the oxygen missing. Or to that deficit, right? The book is defining deficit as just D. Okay, and then we can look at a reaeration rate. So the rate of reaeration would essentially be some Kr times the deficit. So Kr then is the reaeration rate constant. And this will also probably put in per day units. Okay. So then we could take a look at this reaeration rate constant in particular and define some terms about how do we know Kr. So Kr is a physical process. Maybe we can tie it to physical parameters about the river or the waterway. Yeah. Yes. Okay.
Everybody is.
Yeah, we're making do best we can here. And the panel here.
Yeah, I'm just going to put it up manually.
Fantastic. Thank you.
Give me
One quick question. Can I get this to the feed from the laptop?
from the laptop. Yeah. Let's see. It's going to be here.
Okay. Give me a moment. Okay. We're back in business. All right. How many of you are now thankful for PowerPoint? What do you think about the chalkboard? Do you feel like it's makes much of a difference, or maybe it's just me with the chalky fingers? I'm thankful. Okay. So we were talking about this reaeration, and I was just starting to say that this reaeration as a physical process, that's the deficit concept we were talking about. And this is, we can define the KR here based on kind of the physical parameters of our river. So if it's moving fast, if it's splashing a lot, that can all make some sort of an impact. So there have been quite a few studies that just kind of take a look at how quickly are rivers reaerating. Like what happens to be their capability of reaerating. And so people have derived empirical equations that relate to the height and the speed of the river. So these numbers here, this equation, Kr is equal to 3.9 times u to the 1/2 divided by h to the 3/2. That is really just a definition or a determination based on typical rivers. Right? It's not theoretical, it's just experimental, right? People observed it a lot and said, oh, well, if we take the speed of it to the 1/2 power, multiply that by 3.9, divide that by the height to the 3/2, that's a good approximation, right? So people collect a lot of data, took those two parameters and tried to fit everything to it, and they found that was close enough and said, okay, we'll go from there. Okay, so then we have some understanding of our rate of deaeration and some rate of reaeration. And we can recognize that the deaeration has a lot to do with how much substrate was there and how much time has passed. And the reaeration then is relating to the deficit created by that deaeration. Right, so if we go back to the moments where we were looking at the oxygen sag curve compared to the substrate removal, we'll notice that the rate at which we are getting reaeration starts slow and then increases over time, and then as we're getting closer back up to our deficit or to our saturation point, the rate of reaeration is slowing down again. So it really just kind of depends on where we are in that system. Okay, so that's where I was going to leave off and pick up with the next set of slides. Okay. All right, so it's a bit of a question here. Let's see, where was I going with this? I think this was just a clarification from before. So I guess we could ask ourselves, does K for, let's see, the generic K was the K for the BOD removal, right? Is that the same as the deoxygenation K? And it actually, let's see, we'll just have a look at what the book says about this. So the deoxygenation rate constant KD is often assumed to be the same as the temperature adjusted BOD rate constant K from a standard laboratory. For deep, slow-moving rivers, this seems to be a reasonable approximation, but turbulent, shallow, rapidly moving streams, the approximation not so much. Such streams have deoxygenation rate constants that can be higher than the values determined in the laboratory. So basically, sometimes K is equal to KD, but the conditions in the laboratory don't quite simulate what's happening in a rapidly flowing small stream enough to say that for sure. Okay, so a little side note there. All right, so if we take a look at this reaeration rate constant, KR, I've got some values here that kind of give an example of how quickly, or at this reaeration rate constant, what are the typical ranges given different water bodies? So these water bodies, we looked at the speed and the depth, right, as two parameters. So shallow would mean most of the water is exposed to the air. So shallow water tends to have quicker reaeration, right? Faster water tends to have more splashing, more turbulence, more exposure, turnover, all of that. So faster and shallower make for better reaeration. So we'll see small ponds, backwaters, you could say bayous, would be pretty slow, right? 0.1 to 0.23 per day is the rate constants. Large streams, low velocities, 0.35 to 0.46. Swift streams, 0.69 to 1.15. Rapids and waterfalls above 1.15. So you just kind of give a general range. We could, if we had some particular problem, you could grab a value from one of these as an example. So there's a kind of a range of values we could use. Just wanted to take a look at that. Here's just kind of the book's description or demonstration of typical, if we follow the rates itself. At the top, we have oxygen rates. So the rate of reaeration, kind of mentioned this, but it starts off fairly slow. There's not a whole lot of oxygen missing at first. So the rate of reaeration is not happening very quickly. And then it reaches a maximum at the same point where the deficit is at the maximum, right? So the maximum deficit is our maximum reaeration. So we could take a look at these models in a few different ways. Find that critical point, as we'll see it's called, would be right there, shared if we look at the oxygen sag curve and the rate at which reoxygenation is happening. Now, the rate of deoxygenation is dependent on how much substrate's there. So that's just going to be decreasing kind of the whole time because the substrate itself is decreasing. You could consider that, at some point maybe you have another wastewater discharge, and so that would certainly change your model. Something that you could add to your model. So in real life, people managing wastewater discharges are very likely adjusting for, okay, well, we have our wastewater discharge here. We think that's not going to be an impact, but somebody else is illegally discharging over here and making us look like we're the problem, right? That type of thing could certainly happen in real life, right? So these types of models could help figure all that out. Okay, so when we want to model the deficit directly, what we want to do is say we have the dd, so d of deficit divided by dt, essentially that's going to be the deoxygenation rate minus the reaeration rate. So we could then have this equation, so dd dt is equal to kd times L naught e to the minus kt, which we defined earlier, minus kr times deficit. All right, so take 20 seconds and integrate that. Just kidding. So, but that would be the next step, right? So we want to find the a solution for this rate so that we could find d as a function of time, right? So if we can know the deficit as a function of time, that's quite handy. That can let us find at what point do we have the largest deficit, how bad does it get, all of that type of information, right? So we want each piece there in order to know what our system is doing. So the book did this for us so that we didn't have to cry about it. So it turns out this comes to be the deficit is equal to kd L naught divided by kr minus kd, all that times e to the minus kdt minus e to the krt as a unit, plus the initial deficit times e to the minus krt. All right, so we've got quite the equation there. Fortunately, it's all laid out in pieces that we should know something about, right? We should be able to find this initial deficit, or perhaps it's close enough to no deficit, so we could say it's 0 and get rid of that whole term. We know how to find kr, so we'll just say this should be small, typically. Sometimes 0. So we have an equation for kr. We probably know something about kd just given how fast microbes consume stuff. That's kind of what we talked about in previous sections a bit. And we probably know L naught because we've done some sort of measurement, right? So we can know something about L naught or estimate it given a BOD measurement. And so with that, we kind of have everything we probably need, right? We could also just measure the D initial. Just what's the amount of oxygen versus saturation at that point. So, all right, so we have all of those pieces, so we can work with this. There is a bit of an exception, however, if given our stream dynamics and all that, if these two happen to be equal, we have a divide by 0, so we get a problem. That's not necessarily going to be common, but it's something we ought to check. So inherently, the reaeration rate constant, these are just rate constants, right? These are not the rates themselves. The rate constant for kr is just dependent on the stream's physics. The kd is just dependent on the microbes' biological action. Sometimes those could end up equal, and then we have a problem. So if that's the case, so if kr is equal to kd, and only in that case, we have a simplification. So I'm giving you both formulas on the formula sheet so that you can kind of check what's happening and which one to use. So then we could have a simplification to say, well, the deficit can then be approximated by kd L naught times t plus d naught, all that times e to the minus kdt. Okay, so that gives us the deficit at some time. But we still have a question about, well, what distance does that maximum deficit happen? At what distance downstream or time flowing downstream do we have the big problem, right? When we looked at the SAG curves or drew those up, there's always that minimum point before enough substrate's been removed that reaeration starts happening, and the rate of reaeration is outcompeting the deoxygenation. So at some point, we'll be going back up. But at what point is it kind of the worst case scenario? So that we could rearrange. We could find a maximum function for that D and get this critical point. And our book is defining this as T critical, TC, or XC, the critical distance. And so this is going to be essentially the amount of time before we hit that maximum. So we have an equation TC is equal to 1 over Kr minus Kd. We notice again that we run into that same problem potentially. So we might not be able to solve this one in that manner if Kr is equal to Kd. So we have that times the natural log of Kr over Kd times 1 minus this stuff, which is d naught times Kr minus Kd divided by Kd times L naught. Okay, so we have all that, and of course just a quick reminder, we can convert between distance and time just by the definition of velocity is distance times time, or divided by time. Okay. So those are the pieces we need in order to model that oxygen deficit to find what we're really interested in, right? That's kind of the overall scheme of how we go about defining and finding the issues. All right, so let's take a look at an example. I'll get these formulas up for you again in a moment. This is example 5.7, page 213. It says the wastewater in the previous example has a dissolved oxygen concentration of 2 milligrams per liter, a discharge rate of 1.1 cubic meters per second. The river is receiving this water. That is receiving this water has a DO equal to 8.3 milligrams per liter, a flow rate of 8.7 cubic meters per second, temperature of 20 degrees Celsius, and assuming complete and instantaneous mixing, estimate the initial dissolved oxygen deficit of the mixture of the wastewater and river water just downstream of the discharge point. Okay, so this is kind of taking a step back for a moment. We just talked about a lot. Right, we've got this complicated formula. This problem is just starting to scratch the surface on, okay, what does a problem look like? How are we going to start setting it up? Okay, so this one is asking us, pay attention to what it's asking us exactly, and don't automatically assume we need to jump to the most recent equation, right? So take a moment and take a look at that. I think I've got, elaborations from there as well. Bless you. All right, so we should have something that looks like a mass balance on dissolved oxygen. And then from there, we can take this little table up here that's showing us kind of the solubility limits. We're not really given too much information, so we maybe assume that the chloride concentration is 0 for this table. Turns out oxygen solubility does depend on some things other than temperature, like the amount of chloride you have. So maybe there was some information on that in the previous problem. I don't remember, so I'm just going to say no chloride. We'll assume no chloride. And so we can use this value here, 9.09 as our saturation value. But we don't need that until we figure out how much dissolved oxygen is actually in there, and then use that in reference. So to get our dissolved oxygen in the mixture, we can say that should be equal to all these things we know divided by Qm. So we'll say Q wastewater, that's 1.1 cubic meters per second times the dissolved oxygen in the wastewater. In this case, they didn't really re-aerate, I suppose. So that's 2 milligrams per liter, and the river had 8.7 cubic meters per second with 8.3 milligrams per liter of oxygen. All of that divided by the combined flow rate, which would be 9.8 cubic meters per second. Anybody have that solved already? 7.59. Sounds good to me. That is certainly below what the river had and closer to the amount of that was in the river than was in the amount of the wastewater, right? So that seems right to me. Then that would mean our deficit initial for the mixture, this D naught, should be the oxygen at saturation, that 9.09 from the lookup table, minus 7.5. Okay, and that looks like it should be pretty simple, right? That should be 1.5. 1.5 milligrams per liter. So this would be the oxygen deficit. That's our just downstream of the wastewater discharge, assuming it all completely mixed and everything. That's our D naught. Okay, so this is in part just to show you when we're building towards these equations, this would be one of the first steps, right? To figure out, okay, what is the actual deficit right there? Maybe we need a small mass balance, something like this. Again, the type of stuff we've been doing quite often, just this particular case. Okay, so then the next example brings it a bit further. It says just below the point where a continuous discharge of pollution mixes with a river, the BOD is 10.9 milligrams per liter. The DO is 7.6 milligrams per liter. The river and wastewater has a mixture. Wastewater mixture has a temperature of 20 Celsius, a KD of 0.2 per day, average flow rate speed of 0.3 meters per second, an average depth of 3 meters, which apparently continues the previous problem. And it says, A, find the time and distance downstream at which the oxygen deficit is at a maximum, and then B, find the minimum value of DO. All right. So we have just 10 minutes left. This is probably going to take more time than that. So I can do a couple things. I'll give you 5 minutes to start this, and then I'll kind of sketch out the first steps with you. Can also resume and finish this with you on Thursday with the exam review. And I can probably post, if we needed to. If not that, then I could also probably post the actual solutions from the book, or you could just look in the book if you have it. So right now, take a couple minutes to challenge yourself to how am I going to start this problem? How am I going to approach it? I'll take a couple steps with you, and then we'll call it a day there. All right, so a couple things we'd want to be looking at is kind of what are our initial parameters that we're going to use. Even before we really decide what formula to use, I mean, it's to find the time and the distance, we know we're going to need this one. We might as well check KR and KD to make sure they're not equal. If they are equal, then we can't use this, and essentially we can't answer this problem either. So we're going to double check that that's not true. We need to punch in the numbers for this. So if somebody has that, let me know. And by the way, you know, if you think about the units here, they get a little squirrely. As I recall, we're supposed to use meters per second for the speed and meters for the height, and then ultimately somehow that magically becomes per day units for the rate constant. But again, it's empirical, right? So it's just, if given these parameters, here's the answer, like here's a number, right? So because it's empirical in that manner, it's all right that the units are weird. We just trust it. That's just how it correlates. So that should be fine. Every time I teach this, I think back, like, wait a second, this units aren't working. What's going on? But if we were to flip back, I'm pretty sure we'll see that it says the height in meters, the speed in meters per second. Okay, so that would give us KR, KD was given. We can solve for the deficit here, 1.49. It's very close to the last one. I kept wanting to say 1.51, and then I was like, no, that's what am I doing? Okay, so then we have most of what we need to solve this. And then one other piece would be the initial BOD. And if we read the problem, it says just below that point, the BOD is 10.9 milligrams per liter. So we could kind of think of that as like, that's the biological oxygen demand. That's not just a 5-day test. That's the amount that's there, right? So that should be what we're referring to with that. That should be the 10.9 milligrams per liter. And then we could use those pieces to find what's next. Now, question? Yeah.
What's the difference between the D naught in the problem and the D naught we solved for?
Okay, so the D naught we solved for a moment ago here, is that kind of what you're talking about?
Go back to the 9.09 minus 7.6.
Yeah, so this is, in this problem here, we're solving for it because the D naught is the initial deficit after the streams mix. And so, which one are you saying we're solving for? Like,
the 9.09 minus 7.6 versus the D naught is 7.6 it gives us.
Okay, so the 7.6, this is a very good question because it is very confusing. D is for the deficit, and you got to make sure you're not confusing that with the initial dissolved oxygen. So the initial dissolved oxygen, that's the 7.6 in the river there. So the deficit is always the DO at saturation minus the DO at some point. So great question, because that's very easy to get confused there. All right. Okay, so we'll see you on Thursday. You'll probably notice, I think in the homework, we can do a little bit of math with like how much is remaining using that L naught equation. We didn't really touch that here, but it's kind of the same stuff we've been doing with mass balances.